Okay, Chapter 9, Segment 3. So this segment starts with two-tone suppression, which is the rate at which an AN fiber responds to changes when energy is introduced at nearby frequencies. So this means that like the second frequency that is introduced, like once it's added, the rate of neural firing for the first tone decreases, and this phenomenon is more prominent when the second tone is lower in frequency. So next is rate saturation, and that's the idea that the sounds that listeners find more important are heard at frequencies that exceed just detecting sound. So the question of this rate saturation is, are AN fibers as selective for their characteristic frequencies at levels well above their threshold as they are for barely audible sounds used to chart threshold tuning curves? So ISO intensity curves are used to measure an AN fiber firing rate to a wide range of frequencies, all presented at the same intensity level. So what they found with this is that for relatively quiet frequencies, so like 20 decibels, the neuron is still quite narrowly tuned and fires faster, whereas at like 80 decibels, the neuron appears to fire about the same rate for any frequency in the range of 800 to 2500 hertz. So rate saturation is the phenomenon behind broadening of frequency selectivity. So the farther the stereoglia pivot, the faster the AN fiber is linked to that hair cell fire. So next is the rate intensity functions. And rate intensity functions are a graph plotting the firing rate of an auditory nerve fiber in response to a sound of consistent frequency at increasing intensities. So low spontaneous fibers have the resting rate of less than 10 spikes per second as seen on the graph, and high spontaneous fibers fire 30 or more times per second, even in silence. And then mid-spontaneous fibers have resting rates somewhere in the middle. So the auditory system can accurately determine the frequency of incoming sound waves by integrating information across many AN fibers using the patterns of firing rates. So next we're going to talk about the temporal code for sound frequency. So phase locking is when the AN fibers tend to fire action potentials at one particular point in the phase of a sound wave. And this occurs because AN fibers fire when a stereocilla of hair cells move in one direction, but do not fire when the stereocilla move in the other direction. This means that the AN fibers and their firing patterns follow a temporal code. And this temporal code is the tuning of different parts of the cochlea to different frequencies. When reliable for lower frequencies, temporal coding becomes inconsistent for higher frequencies above 1,000 hertz. And this is all due to a refractory period of AN, like the refractory period that the AN fibers have. And now this brings us to the volley principle, which is the idea that multiple neurons provide a temporal code for a frequency if each neuron fires at a distinct point in the period of a sound wave but does not fire on every period. So the way that the book explained this was, think about how they used to fight like the Revolutionary War, how the men on the front line would shoot first, and then the men on the second line would shoot, and then the men on the third line, so that no man was ever firing on the same period twice. So then there was never a time, even in the refractory period, there was never a time where there wasn't men, or in this case, neurons firing. So next we're going to talk about the auditory brain structures. And so the cranial nerve 8 is both an auditory nerve and vestibular cochlear nerve. So that means that it's attached to both the area of the cochlear and the area of the cranial nerve. So all AN fibers initially synapse in the cochlear nucleus, and the cochlear nucleus consists of 3 subnuclei. Some neurons appear to only relay from the cochlea to the superior olive, which is the early brainstem region that preserves accurate timing information. So unlike most other parts of the brain, like say the eyes and the nose, the signals from both cochleas reach both sides of the brain after a single synapse. So what that means is that if you only hear a sound in your right ear, after just one synapse, it reaches both sides of your brain. So neurons from the cochlear nucleus and superolive travel up the brainstem to inferior cochleus. So the midbrain nucleus is an auditory pathway, and the info comes from the opposite ear in midbrain. So the primary auditory complex, often referred to as A1, is the first area within the temporal lobe of the brain responsible for processing acoustic information. So the tonotopic organization is not consistent in the A1 area, and what tonotopic organization is the arrangement in which the neurons respond to different frequencies, are organized anatomically in order of frequency. And so that is not consistent in the A1 area of the temporal lobes. So neurons from the A1 project to the surrounding belt area of cortex, and neurons from this belt synapse with neurons in adjacent parabelt area. In the second auditory areas, simple sounds or sine waves elicit less activity than in the primary auditory complex. So now we're going to talk about basic operating characteristics of the auditory system. So the whole time we've been talking about just the function and the basic overview of the auditory system, but now we're going to talk about like actual human listeners and what they hear. So the study of the human listeners and what they hear is called psychoacoustics, and it's called psychoacoustics because of the acoustics from the actual sound that they're hearing, and the psycho from their own psychological characteristics of how they're hearing it.